Okay, let's begin. So today we are going to learn about two slides. Let's say the training timetable. First slide is technical principle and the application of the intelligent lossless network. So in this slide, we will introduce some basic fundamental of lossless network, such as the working principle of PFC, ECN, and NOF. NOF. So this three technology is very important for in this slide. And next we'll learn cloud fabric, computing and hosting network solution. In this slide, we'll introduce the network virtualization scenario. We have two Huawei solution, computing and hosting. And this slide, we will have some lab and the teacher, Mr. Lin, will show the lab tomorrow for the cloud fabric computing and hosting network solution. And during the class, if you have any question, and you can type your question in the chat room, or you can open your microphone. Okay, let's begin. First, yes, I think you can download the training material in the Harbor Road, because share the link, because I have let me have a check where I can find it. First, I send you a link to download the PDF version, and if somebody of you know the website of the PPT version, you can share in the chat room. First, select the English. The menu with training certification. Start. See the datacom. HCIE data center network. The learning. Okay. From this link, you can download the PDF version. And if you want to download the PPT version, I think somebody of you, if you have the privilege to access the Harbor Zone, I think you can share the link here. Okay. For today, you can just download the HCIE data center network training material, the PDF version first. Okay, let's continue our class. First, let's visit the technical principle and application of the intelligent and lossless network. Here I must tell you, the intelligent and lossless network is just a logical concept. It's just a logical concept. For the lossless network, we will learn some technology, PFC, ECN, ECN, and so on. But before we learn this slide, I will tell you this intelligent and lossless network is just applicable for some special scenario, such as HPC, AI, and storage. Storage. It's just used for special scenario. Okay. As I must make you understand this. The lossless network just for some special scenario, and the technology we learned before today. We see the timetable we learned before today, such as VXLAN, principle, such as SFC, and the virtualization technology. This technology is used to help us to understand what? To understand the VM, understand the VM, communicate with each other through fabric, through fabric. This fabric contains span and leaf, span and leaf architecture, span and leaf architecture. This architecture. So in the HCI DCN network, I think the most important is that we must understand what we learned before today. Okay, we must know VXLAN fundamental. And this lossless network, just in this part, because we all know VM is located in host machine, and this VM is also located in one host machine, And how does host machine and host machine communicate with each other? For example, they communicate from the back end, in this way. All the host can communicate with the storage server. Here is a storage server. The host connected to the storage server, and this host also connected to the storage server. Or maybe the storage server connected to the storage server. So from this part, we can see here, this network, it also uses the span leaf architecture. Okay, it also uses span leaf architecture. But the difference between this part, this span leaf, and this span leaf, the bigger difference is that for this part between server and server, host server and storage server, between these servers, the network need to be lossless. So this technology is focused on this part, because this part, the environment setup is very maybe it is difficult, or maybe it will cost. Its cost is expensive. Because we have special server, and special storage server. It has large volume. Okay, so in the HCIE data center network, we don't have lab for this part. Okay, we don't have lab for this lossless network. Okay, this part. Okay, so that's what I tell you before we learn the technology. I must make sure that you understand the scenario of lossless network. Okay, here it's just for some theory, just for theory. We don't have lab for this part. Although we don't have lab, have any lab or have any experiment for this part, but I think it but I think we also need to learn the principle of lossless network. So let's begin. First, let's say the background that why we need the lossless network. Okay. As a growing number of enterprises around the world undergo digital transformation, the focus of network is shifting from fast service provisioning and to efficient data processing, and to improve. Here we can see here to improve data processing efficiency. Popular applications such as high performance. One scenario, HPC, okay, distributed storage, okay, another scenario, 1, 2, 3, and the AI, uh, uh, artificial intelligence, this is another scenario, this is the third scenario, network with low latency and high throughput. On the server side, traditional data forwarding requires multiple memory copies, which can't meet the preceding application requirements. The host uses RDMA to directly read the data from the remote memory through NIC, achieving low latency and high throughput. However, we can see here the IP network architecture dedicated to RDMA is closed and can't be operated in a unified manner with a traditional Ethernet, resulting in high cost. So that's why we needed to introduce RDMA over Ethernet. That's because the IP network is closed and it's expensive. Okay, so we want to make the IP network, dedicated IP network to Ethernet network, just like we have changed the TDM network to Ethernet, Ethernet network. Okay, the Rocky technology efficiency solves this problem. Currently, applications such as HPC, distributed storage, and AI use Rocky V2 to reduce CPU processing and forwarding latency, improve application performance. However, RDMA is initially carried on a lossless IP network. The IP network is lossless, because it's dedicated and special. It uses special hardware. Okay. Therefore, when Rocky V2 is running on Ethernet, Rocky V2 requires the network to ensure lossless forwarding. And Huawei Intelligent and Lossless Network use AI-ready hardware architecture and a lossless algorithm to provide a network environment with zero packet loss, low latency, and high server output for Rocky V2. Okay. Here I can introduce more about Rocky. Rocky have two versions, and Rocky version 1, V1. Rocky version 1 just run a local area network, and Rocky V2 can run on different network segment. That means Rocky V2 support IP routing. So this sentence tell us the scenario. Okay, so to make a network to be lossless, to be a lossless network, we must have special hardware architecture. Okay, we must have special hardware architecture for the switch, for switch, and the server. Okay, the server must also support the lossless network technology. Okay, they must work together. The server must have smart NIC. Must have smart NIC. Okay, the server must have smart NIC, and the NIC must support Rookie v2, and the switch must also support Rookie v2. Rookie v2. So it means if you want to build a lossless network, you must buy the dedicated switch and the dedicated server. Okay. And this course focuses on the fundamental and typical application for key technology of Huawei intelligent and lossless network. Let's say so this question as I can't answer you because I don't really know when you will practice and prepare for lab. Okay, if you mean the exam, I think you can view the website and sign up for the exam. Then you can participate the HC Data Center lab exam. Okay. So this slide has three parts: development and trend of intelligent lossless network technology. And the second part is the principle of key technology of the intelligent and lossless network. The third part is the typical scenario of intelligent lossless network. This part, part 2, is the most important part. So from the chapter name, you can say the knowledge in each part. The part 1 just describe some basic concept. Okay, so let's first become the first part. The AI area has arrived. The AI has come. Facial recognition, unmanaged driving, and intelligent recommendation are closely related to our daily life, work, and learning. So this all requires the participation of AI. And to implement AI, massive data needs to be collected and filtered, and then an AI training model is established. So after the filtering, the model is trained. With the rapid increase of AI application data, the scale of the AI algorithm continuously increase, and the training task of the AI model requires a massive amount of computing. So we just see this sentence. The training task of the AI model requires a massive amount of computing. Okay, we need a massive amount of computing. But we see the computing hardware. Since 2012, the amount of computing required for the latest model training doubles every 3 or 4 months, and the model training time is prolonged, which severely affects the iteration period of AI model deployment to meet AI service market requirements and shorten the model training duration. High requirements are imposed on AI computer power. We can see this dedicated hardware processed unit. For example, Huawei Ascend 910. This serial. This serial GPU. Serial GPU. And the number is 320. But we can see what we need. We need the capability is 10,000. 10,000. So you can see we have a big distance from the hardware and to what we need. So in order to solve this problem, we can put many GPU together. Okay, we put many GPU work together. Many GPU work together. That's what we named distributed AI cluster. Okay, one is 300, and it will put 10 together. 10 GPU together. The number will be 3,200. Okay, it will be more close to what we need. That's we introduce the AI cluster. Okay, we put many computing. Okay, put many computers together in a cluster. Okay, and if we use many server or many computer here, we must it generate a new problem. We can see here. This is AI cluster architecture. We can see each time the GPU completes an AI iteration, the GPU synchronizes parameter data to the PS. That means the parameter server. For example, first the AI PS, the AI server allocate data to the work node. We have 1, 2, 3, 3 work node here. And when the work node has generated the result, it must send the packet to the parameter server. Okay, here we can see this link is 100 GB, and this is also 100, and this is also 100. And when all the server, this cluster, send the packet to the AI parameter server, it may generate congested. Okay, so to meet the requirements of distributed AI computing, high-speed data center network with zero packet loss needed to be constructed. That's why we need lossless network. Here we see the deployment of storage media requirements with the high performance. We can just see here, just here. In the HDD area, the latency in the data transmission network is 1 millisecond, but it is not the important part of in the for transmission task, but in the NVMe area, we can see here the transmission latency take a great part. So we must reduce the latency of the transmission latency. Okay, we must reduce the green part, the transmission latency. Because the hardware, the disk hardware has improved many times. Okay. So in order to improve the performance of the computing and storage network, we introduced the IB, infinite band IB. IB uses the RDMA technology. You can see here, the packet is transparent from the application directly to the application on the other server without data packet encapsulation. Okay, I think if you remember, in the last week, we have learned the data encapsulation in the Linux system. All the data encapsulation is did in the network, protocol stack, It will add a different header at each layer. But if we use RDMA technology, we don't need to encapsulate the packet. In this way, the forwarding latency is very low. Okay. In this case, memory data is exchanged between servers through dedicated IB NIC. It means the server has special NIC, IB NIC, and the switch is IB switch, dedicated switch, IB switch, achieving low latency and lossless transmission. Dedicated storage network, fabric channel. This network is used for storage. Okay, storage. And this network, IP network, usually is used for computing, cluster, for AI scenario, computing scenario. And for the dedicated storage network, we use a fabric channel, FC network. Traditional data center use FC to construct a dedicated lossless storage network. Therefore, server must use dedicated FC NIC and work with FC switch. The traditional FC technology is widely used in storage area network for its high speed. Let's say the converged Ethernet, efficient and lossless IP and FC. Here, to implement a efficient and lossless storage and high-speed I/O, multiple networks may be established in a traditional data center. Ethernet carries the IP traffic. This NIC, Ethernet, carries the IP traffic. FC carries the SCSI technology. And IB may carry high-speed cluster I/O. Server need to provide multiple I/O interface, different type of NICs. Here we have three types. Therefore, the idea of I/O integration gradually emerges, which is to implement storage and high-speed I/O transmission through one Ethernet NIC. After I/O integration, three networks are converged into the Ethernet, and multiple types of network traffic share one physical link, building a unified converged data Ethernet (DCE). Okay, DCE is also called the converged enhanced Ethernet (CEE). CEE. We build the network all-in-one Ethernet. All-in-one Ethernet. Okay, we use PFC, congestion network, congestion notification, CN. Let's see the development of lossless Ethernet protocols. We can see different program such as in the 2017, the NVMe over fabric is generated. Okay, with a population of high performance distributed computing, high performance storage RDMA, and the application of converged Ethernet lossless protocol such as ECN, explicit congestion notification. This is the full name of ECN, explicit congestion notification (ECN), and priority-based flow control (PFC). Okay, you must know the full name of ECN and the PFC. Okay, let's have second have several seconds here. ECN explicit congestion notification and the PFC priority-based flow control. Okay, you must remember this full name. Widely used. Therefore, the concept of lossless Ethernet comes into being. Lossless Ethernet was first proposed in 2008. It is two basic protocols are ECN and PFC. In addition to technologies on the network side, lossless Ethernet also involves features on the server NIC side, including rookie feature that support RDMA transmission on Ethernet and the NVMe over fabric NOF, feature that supports NVMe transmission on the network. Okay, let's say this is about why we need lossless network, and this part we see the architecture of lossless network. We have 5 layer. We have 5 layer here. At the bottom of the architecture is some hardware layer, ASIC, NP, FPGA, AI chip, and the up layer is the flow control layer. We have some concept, PFC, priority-based flowing control, PFC storm control, PFC data lock prevention, and the congestion control layer, ECN, AI ECN, MPCC, IQCN, and the traffic scheduling layer, load balance, queue scheduling, and the application acceleration layer. We use INC and INOF, intelligent NOF. Maybe when you're first when you see this page for the first time, you may have many questions, but with your question, I think we learn the technology together. Okay. Let's see the 5 part. 5 different part. We first learn flow control, then we learn congestion control, then we learn NOF and scheduling technology and INC. First we see the flow control. Okay, this is the priority-based flow control (PFC). Flow control, the transmission rate between two nodes is managed to prevent the transmitter end from fully occupying the buffer of the receiver end, resolving the fast sender and slow receiver problem. For example, this is switch A and this is switch B. Switch A is the sender and switch B is the receiver. Receiver, sender, sender. So when the buffer usage of a specific priority queue at the receive end, that means switch B, one of the queue is congested on switch B. For example, priority 7 is congested and exceed the PFC threshold, the receiver end send a PFC frame to the transmitter end. It means it will send a PFC frame to tell switch A to stop the traffic in the corresponding priority. Okay, let's see here. After receiving the PFC frame, the transmitter end stops sending traffic to the receiver end. The priority 7 is stopped. And when the buffer usage of a specific priority queue at the receive and falls below the PFC threshold, the receiver end sends a frame to the transmitter end, indicating that the PFC stops. Here we can see two thresholds. One is PFC threshold, one is PFC stop threshold. Okay, so what is PFC stop threshold? That means here that means here when the switch A receives the PFC frame, it will stop send the packet. It will stop send the traffic. Send the packet. Okay, and after a time, because the switch B will send the storage the packet to other device, maybe switch C, SWC, or maybe SWD. So after a while, the buffer is lower than the PFC stop threshold. Okay, reach the PFC stop threshold. Then switch A can send the priority of 7 the packet again. Okay, after receiving the frame, the transmitter end continue send the traffic to the receiver end. Okay, this is the working principle of PFC. So in this picture, I think it's very easy to understand. Okay, so let's continue. This is the PFC frame format. The PFC packet format is as follow. It's a layer 2. Okay, it's a layer 2 packet. Layer 2 packet. It has no IP information. Okay, we see the destination MAC address is 01. That means this MAC address is a broadcast MAC address, and the priority vector and the is carried in this part. Priority enable vector 027. That means PFC only support 8 priority 8 027 027. And when receiving back pressure signal, it means here receive PFC stop, PFC frame. A device stop only traffic in one or several priority queue. It just say here, see here. For example, if this value is E and 7, it means it just stop the priority of 7. And the priority from 0 to 6, the packet will not stop. Okay, so this feature enables traffic of various types to share one link. For priority queue with PFC disabled, if some device can't support PFC, the system doesn't apply the back pressure mechanism. Instead, it directly discards the packet in this queue when congestion occurs. Okay. This picture shows more about the PFC packet pressure principle. Let's say here PFC is used to prevent packet loss caused by congestion. When packets are stacked on an interface due to congestion, the device buffers the packet. That means, for example, this interface will have a buffer. It will buffer the packet. However, the buffering capability of the device is limited. Therefore, when the buffer queue is full, the device needs to instruct the upstream device to stop sending packets, which is called the back pressure. Back pressure is to send the pulse flow control frame to instruct the upstream device to stop sending packets. Back pressure interface is determined based on the inbound interface of traffic on a congested interface. So when packets enters the switch, an inbound interface flag is added to the packet. Okay. For example, here we can see this is the outbound interface. Outbound interface maybe GE001, and this is the inbound interface. It may have two or more interface. Okay. For example, it may be G002, 003, 004, 007, and when the congestion is appear on this interface, it will send PFC frame to all the upstream interface from G002, 3, 7, 4, okay, to indicate the upstream device to stop send the packet. In this way, it may cause other problem. First problem, we call it HOLB. HOLB. So, which is what is HOLB? We can see in this scenario. We have two flow. Flow 1 and flow 2. And flow 1 is forward in this path. In this path. And the flow 2 is in this path. Is also in this path. Okay. Different flow have different file tuple. For example, this is SIP and destination IP. Destination IP1. And flow 2 is SIP2. Another source IP and another destination IP. Okay, but they all have the same priority. For example, maybe they all have the same priority 7. 7. Okay, the same priority 7, but they are different frame because they have different source IP address and different destination address. But when the congestion is generated on device 2, it will send PFC to the upstream device, and device 1 will receive the PFC frame from the interface, because it just consider the priority in layer 2. Okay, it will not consider the source IP address and the destination IP address. So all the traffic of flow 1 and flow 2 will be stopped. Okay, that's because the traffic stop is based on priority. It's based on priority. It's not based on flow. But not based on flow. So to prevent this problem, flow-based congestion control can be deployed. For example, ECN. ECN. Do you still remember the full name of ECN? So ECN can be deployed to reduce the sending rate of flow 1 in advance to relieve congestion and prevent device 2 from sending PFC frame. So here you can just think the ECN, ECN and the PFC These two working, these two technology can work together. Okay, ECN and PFC, it can work together. Okay, let's say another problem maybe caused by PFC. We call it PFC deadlock. PFC deadlock. Here we just see the what is PFC deadlock. PFC deadlock is a network state that is caused by the following situation. Congestion occurs on multiple switches due to a loop or some other reason. Okay, due to a loop or some other reason. The interface buffer usage of each switch exceeds the threshold. The switch wait for each other to release resource, and consequently data flows on all switches are permanently blocked. Okay, so this is easy to understand because when the switch receive PLC frame, it will stop send the packet. Let's say this architecture. It will have three switch. We have three switch. In this architecture, when the interface 1, interface 2, interface 3 all send PFC frame. All send the PFC frame. You can find all the interface in the network will stop send any packet. So all the packet is blocked in this scenario. So we call it PFC deadlock. PFC deadlock. Okay. So PFC deadlock only generate in special scenario. Okay. Then we'll introduce which scenario will generate the PFC deadlock. Let's say typical PFC deadlock scenario. This is the first one. In this scenario, multiple flows are combined to form a loop, form a ring or form a loop. Let's first see here. We have three paths. Okay, we have 1, 2, 3. We have three paths. First we say PC1 to PC3. In this path. Okay, so in this path we don't have a loop. Okay, we don't have a loop. And then we say PC1 and PC2. Maybe PC1 and PC2, the traffic is forward in this way. Okay, and then PC2, PC3 may forward in this way. Okay, these three frames work together. Okay, work together, and it will generate a logical loop. Let me draw it for you. This link plus this link and plus this link. So you can see here, if you just see one of the traffic paths, it is not a loop. Okay, but if you put the three paths together, a loop is generated. So this is a typical PFC deadlock scenario. So for the first time, I think you must understand this scenario, why PFC deadlock is generated. Okay. Then we say another scenario. This scenario is maybe appear in maybe appear in the DCN fabric. So this is leaf and this is span. Span. This scenario is also very special. We can see here in this scenario, PFC deadlock occurs because the NIC of the server PC1 and PC2 connected to leaf switch go offline at the same time. So here is important. Goes offline at the same time. Okay. I think you are familiar with the working mechanism of our switch. The switch learn MAC address. Okay, learn MAC address to build a MAC address table. Build a MAC address table. Okay, if the link is down, for example, if leaf2 receive a packet, receive a frame, and the source MAC is from PC1, and the destination MAC is to PC2. Okay, because the link is down. So for leaf2, this device, although this frame is a unique unicast frame, but for leaf2, because the MAC address table about this entry is disappear. So this unicast packet will become an unknown frame. Okay, unique frame will become an unknown frame for leaf2. So because it's an unknown frame, the leaf2 will flood the packet. We can see here the leaf1 send the PC1 send the packet to leaf1. Leaf1 send the packet to span1. Span1 send the packet to leaf2. Because leaf2 determine this packet is an unknown packet, so it will flood to other interface. So it will send the packet to span2, and the span2 receive an unknown packet. It will send to other interface, and then it will send to leaf1. So this is one path because leaf2 has lost the connection to PC2, and the other path is this way. Okay, is this way. The leaf1 lost the connection to PC1. So if you put the two paths together, it will also become a logical loop. So when a logical loop is generated, the PFC deadlock may be generated. Okay, let's say another typical PFC deadlock scenario. And in this scenario, PFC deadlock is caused by NIC fault. The NIC of PC1 is abnormal and the PFC frame are continuously sent. After receiving the PFC frame, leaf1 send a PFC frame to the inbound interface. Okay. Because the NIC, okay, the NIC of PC1 have one fault. It will always send error packet. I think it's easy to understand. It will always send the error packet. For example, this error packet, unfortunately, it's a PFC frame. Okay, the error packet is a PFC frame. So PC1 sends the PFC frame to leaf1, and the leaf1 sends the PFC frame to PC2. So PC2 will not send any packet. And when the PFC packet is sent to span2, span2 sends the packet to leaf2, and the leaf2 then forward the PFC frame to PC3 and PC4. You can see here, PC3 and PC4 will also stop sending any packet. In this way, PFC deadlock is generated. Okay, that's what we introduced. This three scenario. The PFC data log scenario. Okay, in order to uh, break a PLC data log, we have different ways. One is a different way. Different way. First is PLC data log detection. Detection. Let's see how does it work. After an interface of device 2 receives the PLC frame from device 1, the internal scheduler of device 2 stops sending traffic in a specified priority queue, and device 2 starts a timer. So this is important. Device 2 will start a timer. Okay, will start a timer to detect PLC frame received by the queue according to the configured data log detection and declaration. So if a queue is in the PFC X off state throughout the specified PFC data log detection period, because you start a timer and you configure a period, the system determines that a PFC data log occurs. In this case, the PFC data log recovery process needs to be performed. So this name, the PFC data log recovery process, PFC data log recovery process needs to be performed. So during the PFC data log recovery, PFC frames received by the interface are ignored. Okay, ignore the received PFC frame. Ignore the received PLC frame. That means the device 2 will send the packet to the downstream. Send the packet to downstream. To downstream. The internal scheduler resumes traffic sending or discard traffic in the specified priority queue. After the recovery period expires, the PFC flow control mechanism resumes. If the system still determines that a deadlock occurs in the next deadlock detection period, the deadlock recovery process starts again. That okay. The other way is PFC deadlock prevention. Deadlock prevention. Let's say the PFC deadlock prevention fundamental. Okay. In the link between lib2 and server 2 first or lib2 first to learn the address of server 2 due to a fault. Traffic is forwarded through the upstream interface of lib2 instead of the downstream interface of lib2. Just because it just lost the MAC address. This is a formal traffic path sent to server 2. But because the server 2 is lost, and when the lib2 receive the packet, it will send the packet to span 2, just like this. We call this is the hook shift flow. Okay, received from the network side and forward the packet to the network side too from the other interface, just like a hook shift. A PFC uplink interface group is defined in the PFC deadlock prevention function. You can add a leaf node interface connecting to a span node to a PFC uplink interface group. The leaf node detects that a service flow enters and exists through interface in the interface group. The service flow is a high-risk hook shift flow and may cause a PFC deadlock. If the packet is forward in an interface group, that means it may cause a PFC deadlock. So deadlock prevention will be performed for the hook shift flow. How does it prevent? Let's say this way. It will change the priority on the on the middle device. We can see here. We have two queue, queue A and queue B, and the packet from device 1 to device 2 it's in queue queue B, and that means maybe their priority is 7. Priority is 7, and when the packet receive device 2, device 2 will change the priority to 6, to 6, and then send the packet to device 3. Send the packet to device 3. Okay, you can see here. Because we have changed the priority, changed the priority at the middle device. So the PFC deadlock is prevent, Okay, that's that is the PFC deadlock prevention. Let's see the configuration about the PFC. Let's see some command. Undo DCB PFC global disable. That's enable PFC globally. And create a PFC profile and enter the DCB PFC view. DCB PFC profile. By default, the system provides the PFC profile default. The name. You have a default profile named default. Enable PFC for queue with a specified priority. Priority 0 to 7. Okay. And apply the PFC profile to an interface. In the interface view. And you can also configure threshold. In the interface view. And this is configuring PFC deadlock detection. Deadlock detection. You just see the command after class by yourself. This is configuring PFC deadlock prevention. First, create the uplink group. Create an uplink group. And add the interface to the group. And change the priority. Change the priority here. Have step 1, step 2, step 3. And you will configure PFC deadlock and prevention. This is an example. Lossless service is deployed on host 1 and host 2. As planned, that the service is carried by a queue with the priority 3, and the SCP value of packet is 24. To ensure lossless transmission of lossless service, PFC is configured for the queue with the priority 3. First, we change the priority 3 to 4, and then we change the priority 4 to 2. Okay. We see the configuration roadmap. This page shows configure PFC. We create we enter the DCB PFC view. Priority 3 and 4. We configure priority 3 and 4. Enable PFC function. And we create a port group. And then we make the DHCP mapping. We make the DHCP mapping. Okay. Only one create a PFC uplink interface group. Named my uplink and add interface connected to span 1 and span 2 to the PFC uplink interface group. In the PFC uplink group, my uplink configure lossless backup queue 4 with the DHCP value 32 and the lossy backup queue 2 with the DHCP value of the lossless queue with the DHCP value 24. Okay. And last, you can display statistic with about the PLC data log prevention configuration here. The other concept is for headroom buffer. Let's say in this scenario, we have two different center connect use fiber at a long distance. You can see the packet transform in a long distance. It may have delay. Okay, time delay. It may have latency. That means if this switch send the PLC frame to this switch, because the distance is very long. Okay, this distance is very long, and when the packet, when the first switch, we name it SW1. When SW1 receives the PLC frame, it may have some, it may already pass several milliseconds, and in this milliseconds, the SW1 has sent many packets. Okay, has sent many packets to SW2. So in this way, SW2 must buffer the packet in the time before SW1 receive PLC frame from SW2. Okay, that's why we need the buffer optimization. Let's first see some basic concept. This part. A device buffer space can be used to buffer packets, preventing packet loss caused by congestion due to burst traffic. When the device buffer is full, pod queue can no longer buffer packets, and the excess packets are directly discarded. The buffer space is located in the chip and can be divided into the chip level, plane level, interface level, and the queue level. 1, 2, 3, 4, 4 level. Chip level, plane level, interface level, and the queue level. Okay, the chip buffer space is divided among all planes. Each plane buffer space is divided among all interfaces on the plane, and each interface buffer space is divided among all queue on the interface. We have two types of the buffer. Guaranteed port, promotion, and reconfiguration are not supported. The guaranteed buffer is used to ensure the basic forwarding capability of queue. It allows the queue to still forward some packets, even if the queue can't preempt the shared buffer. And the other is shared port. The allocation mode supports dynamic preemption. Shared ports at the same level can occupy the idle buffer of each other. Okay, this because it's a shared port. Shared port, it can occupy the idle buffer of each other. In addition to the buffer described above, a lossless queue also has a headroom buffer. This yellow color headroom buffer. The headroom buffer is used to store packets received in the period from the time when the local queue sends a PFC notification packet to the time when the upstream device stops sending packet. Because it have have a it have a it have a timing 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 variance. So this prevent the package from being discarded in this period, and the packet will buffer in this headroom buffer. And you can configure headroom buffer. Use these three commands. Okay, AI service. Enter the AI service view and the buffer optimization mode, long distance, and the long distance mode. Different level. Okay, so that's what we introduced for flow control. For flow control, we have introduced the PFC and PFC deadlock. PFC deadlock, and PFC detection, and PFC detection, and PFC storm prevention, and headroom and headroom buffer, headroom buffer. I have introduced this technology. I hope you can remember it. Okay, then let's have a break for about 10 minutes. Have a break. Okay, have a break for 10 minutes. Then we'll continue. Okay, 10 minutes later, we'll begin. Okay, let's continue. So about what we learned today, I think if you have any question, you can just write it down. Okay. Then we start learn the congestion control. For this part, flow control and congestion control is the most important. It is two parts, and the other part, maybe we'll learn it very quickly. Okay. So do you have downloaded the training material? Do you have downloaded the training material? I think if you have downloaded it, you can read it before our class. Okay, let's say the introduction to DCQCN and ECN. So what is DCQCN? DCQCN is data center quantized congestion notification. Congestion notification. Data center quantized congestion notification is currently the most widely used congestion control algorithm on RDMA network. For DCQCN to work, network device only need to support ECN, and other DCQCN functions are implemented on NICs or host. Okay, this is very important. Many functions are implemented on NIC or host, and the network device only need to support ECN. DCQCN can ensure high through output on RDMA network that require zero packet loss, satisfying the high requirements of lossless service. DCQCN can be divided into three parts. Let's say this three parts. Congestion point, CP, congestion point in the middle of the architecture, congestion point, CP. And NP, notification point. This is NP. NP is the receiver end. And RP, reaction point. Reaction point is sender. Is the sender end. Sender end. So the intermediate switch checks the current congestion status when the queue depth exceeds the threshold. The intermediate switch performs ECN marking for packets and forwards the packet to the next hop. You can see here on the middle device, on the CP middle device, you can configure the ECN threshold, and if the packet exceeds the ECN threshold, it will send the packets with the ECN field side. It's just a tag, okay? Just a tag, and this tag is located in the IP toast field. In the IP toast field, because in the toast field of IP header, it have 8 bit, and 6 bit is used for DHCP, and ECN used the other 2 bit, the other 2 bit, and if the other 2 bit, the value is 1, that means this is a packet with ECN tag, okay? ECN tag is located in the IP header, So you can find that the ECN is in the network layer. So do you still remember the PFC? The PFC frame is in layer 2. in layer 2. And ECN is network layer, that means layer 3. Okay. This algorithm is implemented by the NIC of the receiver to notify the sender of the congestion information. In Rockaway 2, congestion notification CNP packet control packets are added for congestion notification. The NIC of the receiver checks the ECN field of each received packet. If the ECN field is set, the NIC sends CNP to the sender. And here, this part, the NP will send CNP packet. Okay, will send CNP packet to RP, to RP. And if RP receives CNP, it will adjust the sending rate to avoid congestion. The RP received CNP, it will slow down the traffic rate. Slow down the traffic rate. Okay, this is DCQCN and ECN. Okay, this is important part. Let's say combining PFC and ECN threshold to relieve congestion. When congestion occurs in a lossless queue of the device and the user uses the buffer size of the queue exceeds an ECN threshold, the device performs ECN marking and forward packets. The middle device send the packet with the ECN field set, and the receiver part will send the CNP packet to the client. The client will reduce the packet sending rate. Okay, sending rate. If the lossless queue on the device is further congested and the used buffer size of the queue exceeds the threshold for triggering PFC frame, okay, then this is the PFC threshold. The device sends the PFC notification packet to the client. You can see here, the device will send the PFC notification packet, and the client will stop sending packet in the corresponding queue. And when the congestion in the lossless queue on the device is relieved and the used buffer size of the queue is lower than the threshold of stopping at PFC frame, the device sends the PFC stop package to the client and will send the PFC stop packet. After receiving the PFC stop packet, the client continue to send the packet in the corresponding priority queue. So I think you must remember and understand this page, because it contains both PFC and ECN. The ECN threshold can be configured by manually. It can also configured by the device itself. We call it AIECN. That means the threshold is configured by the device itself. And this picture, this page shows the congestion control. AIECN adapting to VXLAN scenario. Because the ECN, this red color means ECN is set to 1 1. Because in the VXLAN tunnel, the underlay device in the forwarding path, it just sees the outer label. Okay, it just sees the outer label. So we must move the ECN tag to the outer label in the VXLAN tunnel. But when the packet reaches the egress node, and the egress node will will put the ECN tag to the original packet. To the original packet. Then the server will receive the ECN packet. Will receive the ECN packet. So I think it's easy to understand. It's because in the VXLAN tunnel, the underlay device just see the auto label, auto label. So we must copy the ECN value to the auto label. It's just as the MPLS label in the VPN scenario. Sometimes we copy MPLS EXP to IP. Sometimes copy it to VLAN priority field. Okay. Configuring AI ECN for lossless queue. First, we enter the AI service view, and we load a module file stored in a specific path for the EAI system, and enter the AI ECN view. We assign a queue ID. Which queue enables the AI ECN, and then we input the AI ECN enable. Then we see other. These two parts is not important as ECN and PLC. And ECN and PLC. It's just some unusual scenario. Unusual scenario. Okay. Accuracy and intelligent quantized congestion notification enables the forwarding device to intelligently detect the network congestion based on the interval at which NP sends CNP and the interval between rate increase events of the NIC of RP. The forwarding device proactively send the CNP to RP so that the RP can reduce the packet sending rate in a timely manner. Okay, because the switch is in the middle of the DCQ-CN. CN. Sometimes the NP may not generate the CNP packet in a timely manner. The CP can detect the ECN packet and proactively send CNP to RP. Okay. Let's say the working step. After receiving an ECN market packet, the NP learns that congestion occurs on the network and sends the CNP to RP, instructing the RP to reduce the packet sending rate. If congestion persists on the outbound interface of CP, the NP continues to send the CNP. The accuracy enabled CP records the received CNP and maintains a flow table. Just like, for example, I think if you learn IGMP snooping, okay, IGMP snooping, because it's also configured in the middle device, it will observe the download device and upstream device. So the accuracy the CP device, the CP will record the received CMP and maintain a flow table that contains the CMP information and the timestamp. Additionally, the CP keeps monitoring the congestion status of its outbound interface. When its outbound interface is heavily congested, the CP compares the interval at which CMP are received with the interval between rate increase and events of an RP snake. So it will proactively send the CMP to RP. We can see here we have 3 CMP packets, 1, 2, 3. But the second CMP packet is sent by CP. It's sent by CP. The CP just instead the NP device. Just instead of NP, send the CMP. CMP. Okay. Here. This is the picture of IQCN. Somebody may think another scenario. If the NP didn't send any CMP packet, the NP device didn't send any CMP packet, will the CP send CMP packet to RP? So in this scenario, we have another technology. We call it network proactive congestion control, NPCC. Okay, let's say NPCC background. NPCC is a technology that accurately controls the rate at which a server sends RookV2 packets based on the congestion status of a network device port connected to the server. The DCQCN has the following problem. These 2 problems. The IQCN function provided by the intelligent and lossless network can solve the problem that the sender increases the rate in advance. However, IQCN still relies on the CMP sent by the receiver. This is very, very important here. IQCN still relies on the CMP sent by the receiver. Here. IQCN still relies ECM packet sent by NP. Okay, because it will record the received CMP. Just IGMP snooping. It must receive the IGMP packet or like a DHCP snooping. It must receive the DHCP packet. The IQCN must receive the CMP packet. Okay, but in a long distance communication scenario with a relatively long transmission latency, such as data center interconnect, DCI scenario, this can't efficiently prevent congestion from worsening. To address the preceding issue, the intelligent and lossless network provide NPCC function, which enable network device to intelligently identify the congestion status and proactively send the CMP. We can see here, as is, without NPCC, the DC2, this device will send this is a server. Okay, we just think this is a server in DC2. In DC2, the server send the CMP to switch. The switch send the CMP to destination server. Because this is a long distance. The rate at the source and can't be reduced in time. DCI long distance link consume millisecond level latency. It will be config NPCC. It will config NPCC. The CNP packet is generated by this device. Long distance lossless proactive congestion control is enabled on DCI device based on interface. After congestion is detected, DCI device send the CNP on behalf of the destination end to reduce the rate. The number of CNP is automatically calculated based on the congestion status of lossless queue for intelligent congestion control. Here this is a big difference. The CNP packet is sent by this device. Okay, let's see another concept, NOF. NOF is NVMe over Fabric with the development of modern information technology. Higher storage performance is required, especially with the development of flash memory. The speed of storage meter is increasing. The traditional SCSI protocol can't adapt to the rapid development of flash drivers. A new protocol is in urgent need to implement high performance communication between disks and hosts. The NVMe emerged. The NVMe over Fabric protocol based on RDMA transport layer was launched in 2017. We have three types: NVMe over FC, NVMe over RDMA, over ME over TCP. In Huawei solution, we use this manner. NVMe over RDMA. Why we use NOF? The original FC network that carries storage service has become a bottleneck of the current storage network in terms of bandwidth and latency. The new storage system requires a faster and higher quality network. To address this issue, storage and network are deeply reconstructed from the architecture and protocol layers. The next generation storage network technology, NVMe over Fabric, emerged. Now applies the NVMe protocol to the front-end server host to connect the storage area and the front-end host. The NVMe protocol can replace the SCSI protocol in SAN. Now for technology, NVMe over Rookie. Here it shows how to implement NOF on server, NVMe driver. We can see here to support the NVMe over Rookie, the Linux OS version of the host must support the NVMe over Fabric host driver. Support kernel version is Linux 4.18. Mainstream OS, for example, CentOS 8.0, SUSE 50, VMware 7.0, and a host Rookie transport driver. This is the NVMe driver, and this is Rookie transport driver. To support the smart NIC of NVMe over Rookie, the Linux OS version of the host, and the NIC must support Rookie v2. The kernel version that supports Rookie is Linux 4.7 or later, and the Rookie transport layer. To support NVMe over Rookie, the storage system must support NVMe over Fabric and Rookie v2. Currently, mainstream storage device in the market include Huawei storage, Pure storage. Huawei storage support the NVMe over Rookie. Basic design. Now we just say the NOF NOF will NOF technology use LLDP. Terminals use LLDP extend protocol to send registration requests carrying the service system information. Switch is synchronize the information on the entire network using the NOF synchronization protocol. Here we introduce a new protocol, NOF synchronization protocol, NOF. And we also use LLDP. Okay. Let's say NOF technology. NOF plus storage networking mechanism. First, the server install SSD and Ultrabus plug in on the server. And second, plan address run and VLAN and enable NOF and synchronize zone configuration. We use NOF protocol. The host server and the storage send the registration request for login. File step, notify login status information in real time. Notify the host server of automatic connection establishment. How to plug and in. If you, for example, if you add a new, this is AB, and you add a controller, C, and you add a interface, add a connection to the switch. The switch will use LLDP to discover the storage server, and then it will use NOF synchronize the information to other switch and to other server. When fault occurs, a failure over notification is sent through Ultrabus. NOF technology and NOF information synchronization. It's just like the BGP scenario. We use router reflector. In this way, we also use reflector, but it's not called route reflector. It's just a reflector. Okay. It's based on TCP protocol, but it's not a BGP. Okay, it's not a BGP. It's not a BGP. NOF network, while two devices function as reflectors to synchronize zone information, and the other device function as clients. NOF connection needs to be established between each NOF reflector and each NOF client to transmit NOF packets. However, NOF clients don't need to establish NOF connection with each other, and only need to be directly connected to host. The two NOF reflectors back up each other and don't need to establish NOF connection. NOF connection. So I think here is wrong. Okay, change it. Delete not. Okay, and they need to establish NOF connection between the reflectors. Access device directly connected to host can also function as an NOF reflector. It's recommended that the span node to be preferentially used as actors, as reflectors. If span nodes don't support the NOF feature, leaf nodes need to be used as reflectors. NOF packet are encapsulated in TCP packet and can be used to transmit a link setup message, configuration message, end of fault detection, fault detection. Access port, detection. We use LLDP to detect and use end of to synchronize it, and casting port default. The end of can be work together with BFD. Work together with BFD. Okay. Now technology, zone isolation. To prevent the members in different zones from affecting each other. The zone just like VLAN. Zone just like VLAN. It isolate different isolate different members. You can enable the inter-zone isolation function hard zone. If isolation is not enabled, the IP route of different zones are reachable, and the hosts in different zones can communicate with each other. Therefore, when a member of zone 1 is faulty, service of other zones are affected. After the end of zone isolated take effect, inter-zone host communicate is restricted. Hosts in the same end of zone can communicate with each other. A host can be added to multiple end of customer zone. A host can communicate with each other if the zone they are added to overlap. For example, here the A and C, is in the same zone. So they can communicate. And B 和 D, is in the same zone. And A 和 D, A and D, is in the same zone. So they can communicate. Communicate A and D, A and C, B and D. Okay. This is the configuration for enough. We just skip it. Then we see the scheduling technology. First is static load balancing. Load balancing. First, we see some basic concept. Packets with the same characteristic are forwarded over the same member link because they have the same hash key value. Have the same hash key value in the static load balance. A flow refers to a packet with the same characteristic fields and is divided into multiple flowlets based on a specific interval. Traditional lag and equal cost ECMP usually use per flow load balancing. This mechanism uses the hash algorithm to generate hash key values with the character fields of data packets as hash factors and select a member link among links that are load balanced to load data packets. This load balancing mode based on characteristic fields of data of data packets. This mode doesn't consider the usage of each member link. This mode doesn't consider the usage of each member link, and unbalanced loads of member link may occur, especially when there are large flows. Congestion or even packet loss may occur on member links. We just see here, flow 1 have the same characteristic, have the same source IP and destination IP. Flow 2 is another source IP and destination IP. If the lag work in static load balancing, all the packet of flow 1 is sent on this link. So you can see the offload of this link is very heavy. So in order to resolve this problem, we use dynamic load balancing. I can see here. dynamic load balancing, eLearning mode. Dynamic load balancing has have three modes. Eligible, spray, and fixed. Uh, we just introduce one of the mode, and about the other two mode, you can see the production documentation. Here we can see. This means for flow one, we divide it into two parts. Because packet 6 and 7 and packet 1, 2, 3, it have the time between flow 1, 2 and between flow 1 to 1 is the time range is big than the link than the two link than the link latency latency. So in this way, the packet transport on different link. When they reach SWB, the sequence will not the sequence on SWB will not different. So packet 7 and 6 can transport on link 2 on this link. Okay, we can configure dynamic load balancing. This is the command. We skip it. Another is ECMP dynamic load balancing. The lag is used for layer 2, and the ECMP is used for layer 3. Equal cost multiple paths. Here is an example. Leaf 1 to leaf 2. We have two paths. Path 1 and path 2. If we use ECMP dynamic load balance, the packet can transport from leaf 1 to leaf 2 on different way of our same flow. It was a match this condition. Okay. Let's see another concept. Differentiate flow scheduling. Traffic flows on most network are bimodal, consisting of both elephant flows and mesh flow. Mesh flow are flows with a small number of packets at a low rate. Elephant flow carries a large number of packets transmitted at a high rate. Such flows aim to achieve high throughput performance and are highly tolerant to packet loss. So on the inbound interface, the device groups the packet with the same 5 tuple forwarded by a differentiated flow. Scheduling enabled queue in the same flow. In differentiated flow scheduling, the first n packets in a flow are identified as a mass flow. That means the first packet, some first packet in a flow are identified as a mass flow, and the remaining packets are identified as elephant flow. This is because the protocol packets are mostly sent before data packets. On the outbound interface, the device automatically schedules the identified mass flow to a high priority queue for forwarding. the elephant flow is still forward in the queue with the original priority. We just adjust the mass flow to the higher priority queue, to the higher priority queue. Okay. This is the function of differentiate flow scheduling. This is the configuring differentiate flow scheduling. Last technology is ink. Ink. Let's say the scenario of ink. Scenario of ink. HPC system is built to improve computing speed to a manner of tier operation per second (TOPS) and is mainly used for large-scale scientific data computing, processing huge volumes of data. For example, scientific research, weather forecasting. This is HPC scenario. Message passing MPI is one of the mainstream algorithm in HPC scenario. For example, the MPI package, the MPI alliance and MPI barrier algorithm have been widely used in HPC. We can see we have different algorithm and computer many times. First time server and the second time server and the server translation and last time in HPC scenario more than 80% more than 80% of network traffic is small-sized package whose payload is less than 16 bytes. The forwarding latency of a small-sized packet is close to the static latency of device. Therefore, with the increase of the server scale and the computing volume, the number of server data interaction increases significantly, and the forwarding latency increases continuously, causing growing pressure on the network performance. So, ink reducing the latency of HPC small-sized packet. The ink is short for integrated network computing. Computing transfer some computing process of collective communication from server to switch. And the switch is implement both network data forwarding and high performance data computing. So this is important. The switch will do some computing work. Okay, the switch do some computing work. Ink can ensure low latency in HPC small-sized packet scenario on intelligent and lossless network and reduce the communication waiting time, thereby improving the computing efficiency. Servers encapsulate the data to be computed to an MPI packet and send the packet to the leaf node. The leaf node extracts the packet information and the internal computing model in the switch performs level 1 computing on the data. If the span switch is also configured with ink function, the leaf node can forward the data to span node for level 2 computing. The computing result is then forwarded to the server through MPI packet. So for this function, we just remember the result. Ink reducing the latency of HPC small-sized packet, and the network will do HPC data computing. HPC computing is enough. Okay. For the third part is a typical scenario of intelligent lossless network. Let's see some scenario. First scenario is HPC. HPC scenario. I think you have already know what is HPC. So we skip it quickly. In the PS pyramid server architecture, a cluster has two types of nodes: pyramid server and worker. Worker node. The workers are responsible for computing. The servers are connected and responsible for unifying the parameter of all workers in each interaction. Iteration. Workers obtain parameter from parameter servers and then return the computing results to the parameter server. The parameter server aggregates the return data, update the parameters, and then broadcast the updated parameters to workers for the next round. So the network between server and worker must be lossless network. That is most important. You just need to know where the lossless network is implemented. In HPC scenario, it's implemented between PS server and PS worker. Another scenario is AI computing overview. It's almost the same with HPC. Okay, you just read this sentence after class. Then the other scenario is distributed storage scenario. Storage scenario. We can say storage node. Storage node. This part here. This part, not this part. It's this part. We use lossless network. Lossless network. And this is the centralized storage scenario. Centralized. This is traditional span-leaf, and the lossless network is deployed between centralized storage server. Centralized storage server. Okay. This is the fall scenario. For the lossless network. For lossless network. Okay. Let's see a simple question. How many queues does PFC support? The answer is 8. It's 8. 0 to 7. So this course describes the technology and the principle involved in Huawei's intelligent and lossless solution, including PFC, ECNOF, scheduling, and ink technology. So after this class, I think you must remember PFC, remember ECN, and remember NOF, and scheduling, ink, and other technology. You just need to know the concept, okay? Then it is enough. So that's the end of this slide. The end of this slide. Then we have a long break. For 30 minutes. 30 minutes. Okay, we have a break for 30 minutes. Only available in CE. Only a Siri device supported. Let me see. Let me tell you how to find it. Okay. Oh, anyway, enterprise network language to English. Enterprise network 认为select switch data center switch. Okay, you can see here only this type, cloud engine, 128, and this two, is two theory, not all theory, just this two theory support, support the lossless network. Okay, for CE and S theory switch is don't support. Okay, we all have a break, for 30 minutes. Then then we learn the other slide. This slide. Okay, let's have a break.